Well, thank you everyone for coming. I thought what we'd do now is essentially just repeat essentially what Neil said, but with a few more details and places. Okay? So I'm going to talk about 3 or 4 different reasons why you might want to use Gaussian processes. Okay? The motivations people have for using them, why they're so popular. Along the way, we'll kind of think about some of the mathematical details that make them useful. Okay? So it's kind of some large points with some kind of detailed, tedious algebra in place, but I think it's interesting to see it once, right? To show how to do this derivation and so on. And then, if I've got any time left, I'll talk about a few kind of applications in uncertainty quantification at the end, which is a field I work in, which is Neil mentioned at the end, where you got a complex simulator and we use kind of Gaussian processes to approximate them and so on. The main thing is why are Gaussian processes a useful family of model, essentially. So why use Gaussian processes? Well, let's first think about what they are. Okay. So again, this is familiar to everyone, I'm sure, but what's a stochastic process, first of all? So a stochastic process is just some object, I'm calling it f here, okay, and that's indexed by some index, okay, so I'll call that x here. It just takes values, yeah, and it has some distribution. So typically we might think of this like a function. X might be location or time or something like this, but a stochastic process is just some object, possibly infinite dimensional, that's indexed by something. Okay. So usually, as we say, it might take values in real line, although Nicola was telling me that he's doing Gaussian processes on graphs at the moment, so it doesn't have to be in the real line here, and certainly not in general for stochastic processes. And typically your index set might be some kind of Euclidean space. Yeah. So we might think of x as location on a map, so a 2-dimensional number, your coordinates. Okay? And f of x is the value of the function at that location. So maybe f of x is elevation, yep? And x is your position, and so you're describing this surface f of x. Okay. And a stochastic process just means it's a random variable, and we're going to want to model with it. Yep. So, first of all, often f is an infinite dimensional process, so that's tricky for us. Yep. We don't like dealing with infinite dimensional things. That's not a nice thing to have to deal with. We can't keep track of everything. Okay? But thankfully, for stochastic processes, all we need to consider are the finite dimensional distributions. So in other words, its value at a finite number of locations. Yep. So if we can write down for any stochastic process all its finite dimensional distributions. Okay, so in other words, what's the distribution of f at n different points? Yeah, and we can do that for any set of n points. Okay, then we've specified the entire process. So all we need to be able to do is specify the finite dimensional distributions, and that kind of uniquely determines, subject to some kind of measure theoretic argument, the entire infinite dimensional stochastic process. Okay, so that's stochastic processes in general. What's a Gaussian process? Well, a Gaussian process is just a stochastic process which has Gaussian finite dimensional distributions. Okay, so if this law here, if this distribution is Gaussian, then a stochastic process is a Gaussian process. So in other words, if we look at the value of f at any finite set of points, it has a multivariate Gaussian distribution. Okay. In other words, you're familiar with multivariate Gaussians, I guess. So, yeah. So we have some mean vector mu, and some variance covariance matrix, which is an n by n matrix. Okay. So Gaussian process is a stochastic process where if we look at its value at a finite collection of points, it's Gaussian. And that's it. Okay. So this sounds like quite a restrictive class of model. Yeah, as you know, the questions pointed out before. Why would you want to use this? Okay. Why Gaussian processes? Why not more complicated processes? So I'm going to give you 3 or 4 different kind of takes on this. Why this in particular is a useful class of model. Why Gaussian processes are useful. Okay. Well, the first thing is they have several properties that make them nice to work with. Okay. So one property of Gaussians that we like, okay, is that any linear transformation of a Gaussian variable is still Gaussian. So Neil mentioned this. Yeah. So if x is multivariate Gaussian, the dimension n with some mean mu and some variance matrix sigma, then ax is Gaussian, where A is just any arbitrary matrix of the right shape. Okay. And all we do is change its mean and its variance matrix. And in fact, it's an if and only if statement. So x is multivariate Gaussian if and only if A of x is Gaussian for all A. Yeah. So that's a nice property because we get things that we might want to do when we're modelling for free, essentially. So this tells us sums of Gaussian are Gaussian. Yeah, so if I let A be a row vector of 1s, A times x just be the sum of all the x's. And so that says the sum of Gaussians is Gaussian. Fine. Yeah. We also get the marginal distribution is Gaussian. So we've got two variables, x1 and x2. Yeah. And if I let A just be 1, 0, they have x1 and x2 have a multivariate Gaussian distribution. If I only observe x1, it's still Gaussian. The marginal is Gaussian. Yeah. So that's going to be useful in that these are kind of operations that we often want to do when modelling. Okay? So that's one nice property, and there aren't many distributions that have this property. Okay. Possibly the more important one, and the one that will linger on longer, is this idea that they're closed under conditioning. Okay, so we're doing this just for Gaussian distributions at the moment, but because it's true for Gaussian distributions, it's going to be true for Gaussian processes, because Gaussian processes are just things that, when you look at a finite number of points, they're Gaussian distributions. Yeah, that's all it means. So what's this closure under conditioning? Okay. So let's suppose we have x, which has two parts in x1 and x2, okay? And these could both be vectors, if you like. X1 could be a number of observations, x2 could be a number of observations. And let's suppose that jointly they have a Gaussian distribution with some mean vector mu and some covariance matrix sigma. Okay? I'm just going to partition these things in kind of the way that corresponds. So the mean is going to be broke up into a mu1 and a mu2, corresponding to x1 and x2. And similarly here, so sigma 1, 1 is the covariance matrix of x1, sigma 2, 2 is the covariance matrix of x2, and sigma 1, 2 is the covariance between x1 and x2. Yeah. So it's just a jointly multivariate Gaussian distribution. The really nice property about Gaussian processes and about Gaussians is that if we observe part of our vector, the distribution for the part we didn't observe is still Gaussian. Okay? So suppose this is our model for x, someone comes along and tells you the value of x1. Yeah? What now do we believe about x2? Yeah, how should we update our model, in other words? Yeah, what do we now believe about x2? What's our model for x2 now? We know the value of x1. It's still Gaussian. Okay? So all that changes is it's still a Gaussian distribution, the distribution x2 given x1, still Gaussian. We've just got a new mean and a new variance. Okay. And it's this property that makes Gaussian processes so useful, because we can start off with some generic specification of what the data look like. Okay? Train them on the data really easily, and all the training are these linear algebra operations. Yep. And dead simple doing linear algebra. There's no complex MCMC or anything like this. It's just this simple linear algebra. Okay. So I thought what we'd do, just because it's useful to see it once, is just go through the calculation of this. Yep. Some people have probably seen this before, but we may as well just think about it briefly. Okay. So what we want to do is think about the distribution of x2 given that we've observed x1. Okay. So we've got Bayes' theorem here, essentially. Well, it's not Bayes' theorem, it's just conditional probability definition. Okay. So the density of x2 given x1 is just the joint density divided by the density of x1. Okay. But what we're going to do is we're going to look at what it looks like and guess the right distribution from its shape. Okay. So all we need to keep track of are the x2s. I don't care about where x1 appears in here. I just need to know what the x2s do. And so this is proportional to the density of x1 and x2. Okay. So let's write this down and just throw away the x1 bits and just keep track of the x2s and see if we recognise the shape. So if this is the joint density, yeah, this is the joint density of x. Yeah. So remember this is x1, x2 minus mu1, mu2 transposed sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2 inverse times by the same thing, x1, x2 minus mu1, mu2. Yeah, so that's what this bit is in here. That's all that is. Let's look at that. Well, if we kind of think about what happens when we expand this out, okay, and remember we don't care about x1 here, we only care about keeping track of the x2s, we're going to get this x2 minus mu2 times q22, okay, as I've called q the inverse of sigma. Yep, so there's an inverse here, so let's rewrite that. Instead of inverse sigma, let's write this as q11, q12, etc. Yep. If we think about what this is when we expand this out, we just get a term that's squared in x2, so x2 minus mu2, q22, plus the cross term, if you like, and we get this 2 x2 minus mu2, q21, x1 minus mu1. Okay. So we conclude from this straight away that x2 given x1 must be Gaussian, right? That's what this tells us. What we've got here is that the form of the density for x2 proportional to some constants is a quadratic in x2. Now we've got an x2 squared plus an x2, yep. So it's just a quadratic in x2, so this must be a Gaussian distribution for x2. Yep. So all that we have to do is work out the mean and variance now. Okay. So this is just the same thing copied over. Yep. So let's just collect the terms. Pretend it's an undergraduate lecture. Okay. We've got the x2 q22 x2 term. Okay. Then we've got an x2 q22 mu2 term, and then we've got the x2 q21 x1 minus mu1 term. Okay. So that's all we care about. Everything else just disappears in the proportional sign. Yeah, okay, it's just got x1s in and things we don't care about. So just complete the square, essentially. Okay, and so what we get is that we've got x2 minus something times q22, because that's the term in here. And the something we're minusing is half of this term, just completing the square, so we get q22 mu2, well, this bit written here, okay? And the same thing over here, yeah? All I've done is complete the square, and now you can see this is in a Gaussian, the form of a Gaussian density, yeah? So what does this say? Well, it says that x2 has this as a mean, and this is a the inverse variance as its precision matrix. Yep. So we've derived we've shown it as Gaussian, derived the mean and variance in terms of this Q2. Now you just need a bit of matrix algebra to work out what these bits are. Well, there's Google it. Okay, there's you can show it in half a page, but it's easy to show that if Q, remember, was inverse sigma, it's easy to show these things. Okay, you just look them up in your matrix cookbook or whatever. Yeah, and if we plug that in, we get the form that Neil talked about before, given us the distribution for x2 given the observation for x1. Okay. So the new mean of x2 is the old mean plus how surprising x1 was, so how far it differed from its mean, kind of rationalized by its variance, so how surprising it is that we got this deflection from its mean, plus a term that kind of tells us how much information there is in x1 about x2. Yeah, so that's what the covariance does, tells us how informative x1 should be about x2, and this tells us how surprising the x1 observation is. So a new mean and a new variance. Okay, and that's all it is for the derivation, but it's kind of useful to see it once, I think. Okay, so what does this mean for Gaussian processes? So now let's suppose that f is our Gaussian process, yeah, like we started with. And I've not talked about how we find these means and variance matrix yet, but let's suppose that the joint distribution of f at these points. Okay. So what I'm imagining is we've got x, and I've got a number of points. This might be x1, this might be x2, okay, this might be x3. Okay. This is f of x. And we're supposing that jointly they have a Gaussian distribution. Okay. And then I've tagged on the end a generic f of x, okay, which is just my what I think about the value of the function at some other place. Yeah. So we're going to say, what is our belief about f of x given that we've observed the function at these three locations? Okay. Well, we can do that now. Yeah. We started off, the Gaussian process model makes the assumption that jointly they're Gaussian. When we observe the values, our belief about f of x is still Gaussian. Yeah. All we have to do is update our mean and variance. We started off with some mean and variance here. All we have to do is use these formulas to tell us the new mean and the new variance. Yeah. So our belief about f of x, where x could be any point, yeah, given the observations, is just Gaussian with some mean and some variance. And so the picture to have in your head, or the picture I have in my head anyway, is that to make more sense we've done covariance functions, we start with some model of functions. Yeah. So generic class of model, and we'll talk about this a bit more in a minute. Okay. So some wiggly lines. We observe the lines at these locations, and we update our beliefs to get some kind of posterior specification. So we're going from our prior to our posterior. Okay. That's one way of thinking about these things. And we'll see more detail in a moment. So what we've not said so far is where this mu and sigma come from. Yep. We know that if they're Gaussian, we can do the conditional updates. And we're saying that for a Gaussian process, it always will be Gaussian. So how do we determine what mu and sigma are? Where do they come from? Okay. Oh, okay, sorry, there's one more slide just to summarize that. But so, yeah, just to summarize then. So why are we using these Gaussian processes? Because they're closed under various operations. So they're closed under addition. Add two Gaussian processes, it's still a Gaussian process. They're closed under Bayesian conditioning. Yep. So observe the value somewhere, it's still a Gaussian process. Okay. And they're closed under any linear operation. Okay. So we've already said already they're closed under multiplication by an arbitrary matrix, constant matrix, yeah. Or adding them, they're closed. They're also closed under operations that we can do on infinite objects like differentiate them, integrate them. So the integral of a Gaussian process is still a Gaussian process. The derivative of a Gaussian process is still a Gaussian process. Okay? So it's this closure under these various operations that means why we like Gaussian processes. Yep. The fact that these three things mean that we can do what we like with our model once we've specified it. Yep. It might not be the best possible model to begin with, but we can work with it. Okay. We can work with it. We can do stuff. Okay. So the point I was midway through making, how do we determine the mean and covariance? Okay. So our mean here, I'm now going to call this the expected value of fx, this is our mean vector mu. Okay. This is our covariance between any 2 points. How do we determine our mu and our sigma for any collection of points? How do we specify what they are? Okay. And the simplest answer is we try some stuff out and see what we like. Okay, there's some rules we have to follow. Yeah, we can't just pick any choices for these things, but generally there's a small number of candidate choices that you'll see lots of this week, and we tend to try values according to what we understand about the situation. Okay, we'll try and build you that intuition about what kind of choices are going to work well. Then we do trial and error. Basically, you fit it to your data and see does it work well. Okay. So for the mean function, there's no rules. Yeah, we can do whatever we like here. So to determine this mean vector mu, you're basically just limited by your imagination, okay, and the degree of complexity you like. So you're limited by your imagination. So machine learning, they tend to use 0. I don't know what it says about machine learners, but whereas in statistics, we do much more complicated things. So Neil's not here. I'm insulting someone who's not here. It's, never mind. So every year we have this argument at this workshop about whether you should have a mean function or not. Okay? It kind of depends upon what type of data you're modeling. If you've got loads of data, okay, then and you're not extrapolating too far, then having a mean 0 is often quite a sensible choice, or just a constant. In statistics, we're often extrapolating a bit more, have sparser data, fewer data points, and then often it can help to build in some kind of structure, and so we might have some mean function here. And some communities go to kind of a great length to build a complex mean function here, but the most common choice is like linear regression. Yeah? So you think about your linear trend capturing the first order effect, and your Gaussian process is there to mop up all the non-linear fancy stuff that goes on. Okay. The mean function is easy though, you can do whatever you like. You have to deal with the parameters you introduce, so if you use a mean function you've got to estimate those parameters, and that's problematic, but you can do whatever you want. The covariance function is a bit trickier. So we usually use a function that's a distance between the locations. Okay? So we can use whatever we like for sigma, as long as it's a valid covariance matrix, but specifying valid covariance matrices turns out to be difficult. Okay? So what we tend to use are what are called covariance functions, and they're functions of the distance between the two indexes. Okay? So we say the covariance between f of x and f of x prime, where x and x prime are two different points, is just some function of x and x prime. Often it's just a function of x minus x prime, so it's just a function of the distance between them. Yep. Stationary covariance function. And there's rules about what covariance functions we can use here. Primarily that it has to be a positive semi-definite function. Okay? So Nicola, I think, will talk much more about this afternoon, but it's not easy to write down valid positive semi-definite functions. Okay? So what does it mean to be positive semi-definite? Okay? It means that if we've got a collection of points, x1 to xn, okay, and we let sigma ij be this covariance function, the distance between xi and xj, yep, so that just populates this matrix. It means that sigma has to be a valid variance matrix. So it has to be a positive definite matrix, have positive or non-negative eigenvalues. Yep. That's what it means. And it's not easy to write down good functions. So what we tend to do is use a small number of building blocks. We know of a good number of valid choices, and we know that we can combine them in interesting ways. So what we tend to do is kind of match some basic properties, which I'll talk about in a moment, and then kind of experiment a bit. Okay, so some basic covariance functions. The most common one is this RBF, radial basis function, or sometimes misguidedly called a Gaussian covariance function, because it looks like a Gaussian density. Yep. It's not a good name for it. Or squared exponential is probably the most common choice, but Neil hates that. So I think here there's a three-line whip to call it exponentiated quadratic, right? In that it's not a squared exponential, it's the exponential of a square. Okay, so, but he's not here, is he? So I can do whatever I like. So squared exponential. Okay. So this covariance function often is parameterized in some way. Okay. So often there's a number in the denominator here and another number at the front, and we'll see, we'll deal with lots of these things over the next few days. And these numbers determine the type of functions that are generated. So what this picture is are just random functions drawn from the distribution defined by this covariance function. Yep, so I've got a zero mean here, and I've supposed that the covariance function is this, okay, and I've said sample a value of f of x at all the locations along here. We know it's jointly Gaussian. Okay. I've determined this covariance matrix by this. Okay, so it's the same covariance matrix for every one of these curves. This is just a random pick. Yep. And so you can see they kind of wiggle a bit, but not too fast for this particular choice. Okay. So often we make this a bit more complicated by adding parameters. So we add something at the front, a variance term, and something in a denominator here called a length scale, and that changes the kind of feel of these functions, the wiggliness of them, if you like. So here I've used what's called a length scale of 0.25, okay? And so I've said essentially here the function varies over order 1. Yeah, 1 is a big distance here. Okay? I've divided that by 4, so that now 0.25 is a big distance. Yep. And so you can see they've got wigglier. Essentially, they vary up and down faster because I've shortened the length scale, and so we've made the speed at which they can vary. The correlation drops off quicker. Yep. So here, the correlation between 0 and 1 is e to the minus a half. Yep. Here, the correlation between 0 and 1 is what? I can't do that in my head. E to the minus 16 or something like that. It's much smaller, yeah? Minus 8. Okay. If we make the length scale bigger, okay, so now the correlation's much higher. You know, the correlation between 0 and 1 is larger. So we've got a length scale of 4. They vary slower again. Okay. So that's one parameter we change. Another parameter we might change is this number out the front, and that kind of the variance term. And all that does is change the y-axis. Okay. So if I go to this plot, the values vary between about minus 2 and 2. And this plot, they're exactly the same curves. They now just vary between minus 20 and 20. Because all I've done is multiply the variance by 100, or the standard deviation by 10. Yep. And often we have to learn these numbers. Okay. So that's one covariance function, one particular type. One thing you'll notice about these curves is they're very smooth. In fact, they're infinitely differentiable. They have derivatives of all order. Yeah. So a different covariance function are these Matern class of covariance functions, and there's a whole class of them. Yeah. So I'll just pick one of them out here. This is Matern 3/2, and it doesn't really matter about the shape. You never have to think about these things. But this is gives only once differentiable functions. Okay. So this type of covariance function, these wiggly lines are once differentiable only. And so there's rules about covariance functions. Okay? We have a whole classes of them, and some of them are infinitely differentiable, some of them have 2 derivatives, some of them 3 derivatives, some of them are nowhere differentiable, etc. Okay? And so we tend to start by picking a covariance function according to how differentiable we think our underlying function might be, and then kind of take it from there. We can have Brownian motion. Yeah? So Brownian motion is an infinitely, or the Wiener process, it's an infinitely variable process. Yeah? So you could, if you pick an arbitrarily small section of any one of these sample paths, and you can find the complete works of Shakespeare in your own handwriting, yeah? Because they're infinitely variable. So they're nowhere differentiable, okay? And the variation is unbounded. Okay? So that's this covariance function. And what you're probably realizing by now is that it's very hard to guess from the mathematical form of the covariance function what the sample curves are going to look like. I have pretty much zero intuition by looking at these things about what the curves are going to look like before I plot them. Yep. There's some mathematical rules that we can use that help us, but generally you build it up by trial and error. I mean, Nicola probably sees these things in like a no, or yeah, you intuit from the form.
Yeah, when the kernel is stationary, for example, you can look how many times different.
Yeah. That's a mathematical trick, essentially. So I think I've got that somewhere. But let's do a couple of others. So this is white noise. So this is saying that there's no correlation at all. Yep. That 2 points at different x locations are uncorrelated. So they're independent of each other because they're Gaussian. So it's just white noise. Yeah. 1 point and the point next to it are completely independent. So it's just noise. Yep. Okay. So the covariance function is the most important part of the Gaussian process by far, yeah? In that the GP, kind of the Gaussian process inherits all its properties. So things like smoothness, okay? And that's from its length scale, if you like, how quickly it varies. It's differentiability. So as Nicola said, you can work out the degree, the number of derivatives that the sample paths will have by looking at the number of derivatives the covariance function has at 0 if it's a stationary function. Okay. So if x prime is kx minus x prime, it's stationary. Yeah, doesn't matter where you are, you can translate left or right. And the number of derivatives of this thing at 0 determine how differentiable your sample paths are. But we've got these kind of mathematical rules for intuiting these things. And it does things like the variance of your sample paths. Okay. So one final example, is just to motivate the next way of looking at things, is if I use this particular kernel here, that the covariance between x and x prime is just x transposed x prime, so the inner product between x and x prime, all the sample paths are just constants. Okay? So it's kind of interesting to think, why is that? Okay? Why is that happening? Okay? It's really hard to figure it out by staring at this thing. Okay? but we're going to use that to motivate what's coming next. Okay. So, the first answer, I guess, then, to why use Gaussian processes is because they're mathematically tractable, yeah? Because we can do stuff with them. Yeah? The second answer as to why we should use Gaussian processes or might want to use Gaussian processes is that they generalize linear regression. Okay? So in linear regression, you write down what you think your model is and you estimate a finite number of parameters. Okay? So like a straight line. Yeah? Gaussian processes are essentially the non-parametric generalization of that, or the kernel regression. Okay. And in particular, it helps us think about what k means, what the covariance function means. So k determines what kind of shapes we get when we do our linear regression, essentially. We can think of Gaussian process regression as doing linear regression in some higher dimensional space of features, where that space of features we're working in depends upon the covariance function k. Okay, I'll show you a very simple example of this in a minute. But first of all, we'll start by thinking about linear regression, yeah? And show how, with a bit of work, we can see linear regression to be the same thing as Gaussian process regression, just with a particular choice of covariance function. And what we're going to find, in fact, is that it's this covariance function. This is the covariance function for linear regression. Okay, so the situation we're imagining is that we're given our data sets. Okay? So we've got xy pairs, and the x's might all be vectors here. Okay? We're going to put them into a covariance matrix, x, so it's going to be x1 transposed, x2 transposed, etc. N transposed. Okay? And we don't want to do linear regression. So I'm assuming everyone's familiar with linear regression. Yeah? We're going to assume that y is just some linear combination of the x's plus an error term. Okay. So how do we estimate the error, the parameter vector beta? Well, one way is to minimize the sum of squares. Okay, so to minimize the data misfit, so the distance between y and the model prediction. So this is the sum of the squared errors here. Okay. And perhaps we want to do ridge regression. I've done it in a ridge regression way here, doesn't matter. We're going to say, well, we don't want the parameters to be too big, so let's add some penalty term to the parameters. So this is called ridge regression or Tikhonov regularization, or there's probably a fancy machine learning term for it. Is there? I don't know, L2 regularization or something. So this is linear regression. Yep, this is all we're doing. So how do we solve this? We've all seen this in an undergraduate course, I'm sure, that the least squares estimator or the ridge regression estimator of beta is x transpose x plus sigma squared I, x transpose y. Okay. Now with a bit of work, we can rewrite this as x transpose x transpose plus sigma squared I inverse y. Okay, so how do we do that? So I think if we have x transpose plus sigma squared I, am I going to get in a terrible mess doing this? Probably. X transposed. Okay. This is the yeah. Let's do that. This is the same as x transposed. Oh no. No, I'm going to get a mess. I'm not going to dare do that. Okay. We can rewrite it in like 2 lines. In private, I could do it in like 30 seconds. Here, it'll take me about a week. Okay. But I'll write it on the board afterwards. Okay, while you're having lunch. It's really easy just to rewrite this as this. You don't even need your matrix cookbook. It's just 2 lines. Okay. And this is called the dual form for the estimate of the parameter beta. Okay. So we've not changed anything. I've just rewritten it. So at first, this looks like we've made the problem harder. Okay. My X matrix is n by p, number of cases by number of covariates. Yeah. So here, I've got x transpose x in the normal regression form. So that's a p by p matrix. And so I've got to invert a p by p matrix. Here, I've got x transpose, so that's an n by n matrix. So I've got to invert an n by n matrix now. Normally, we have more data than covariates. N is normally bigger than p. So normally, we like to work in this form because p is smaller than n, and so it's cheaper to invert a p by p matrix than an n by n matrix. Yep. But there's an advantage of writing it in this way. Okay. So this dual form makes it clear that this is an inner product method, which I'll define in a minute. This only uses inner products between our covariance vectors. It doesn't use anything but inner products. It turns out lots of statistical methods are inner product methods, and so they can be generalized in the same way we're talking about now. Okay. So let's just see that it's inner products and then think about how we can generalize it once we've realized it's inner products. Okay. So what do we do in linear regression? Well, let's suppose we want to predict y at some new location x prime. So our prediction of y at that new location will be x prime transpose beta hat. So if I write that in with a dual form, we get this here. Yep. Just our prediction. Now this is where we have to squint a little bit. Okay. We'll rewrite this as k of x prime for this term, in that, let me write down what this was again. X was x1 transposed, xn transposed. Okay. And so x prime transposed, x transposed consists of x prime transposed x1, x prime transposed x2, x prime transposed xn. Okay? So it's just inner products between the test location and the training points. That's all it is, just this inner product. Similarly, x transposed is inner products. So if we look at that ijth term of this is just xi transposed xj. Yep. Just inner products. Okay. So why is that useful? Well, it's going to be useful because we can generalize, switch out this inner product for any other inner product we like, as long as we can afford to do so. Okay? And we're going to, we're describing the kernel trick here, essentially. Yeah? We're going to switch out inner product in this space we started with to some inner product in some richer space. And all that matters is that we can evaluate inner products. We don't need anything else just to be able to do that. Okay. So just one final point about this before we move on. Just notice the similarity here between the Gaussian process regression, okay, or what we started with, and what we just derived for ridge regression. Okay. For the Gaussian process, if we had y prime was, if we started off by assuming it was normal with mean 0 in this covariance matrix, then the expected value of y prime given y was given by this. Okay. And if we had, this is our covariance function, it's exactly the same as we just derived. Okay? So the ridge regression we just looked at is exactly Gaussian process regression, or conditional Gaussian process, with this particular choice for the kernel. Yeah? We've not done anything yet. We've just done Gaussian process. We've just done ridge regression. Okay. So let's think about why it's useful to write these things as inner product methods. Well, we know for linear regression you can replace x by a richer feature vector. Yep. So if you've got data that look like this, okay, we don't have to fit straight lines, we can fit quadratics to them. Yep. So we can raise x to a set of features by adding as many as we like. So perhaps we do add an x squared feature. Yep. Then all the calculation of the parameters doesn't change. Now we just our vector k, which is our covariance matrix in here. I apologise, I'll change like our kernel matrix. Okay, is now just the inner product between these sets of features. Nothing's changed. We're doing exactly the same equations, just with a longer vector of stuff here. Okay. Okay. So mathematically, it turns out that for some sets of features, okay, doing this inner product is just equivalent to evaluating some simple kernel function. Okay. So the entire idea behind many of the kind of kernel methods is that you can write an infinitely long set of features here, okay, but you never have to calculate them. All you ever have to do is evaluate this kernel function. Okay. You can write as many things as you like in here, as long as when you come to do the inner product between two feature vectors, it's just a simple mathematical formula. Okay. So this is like doing linear regression with thousands, millions, infinite number of terms here. The trick at the end is to find those features that mean that when we do this, it's just a simple function. Okay. And so because we can do this, because we can use infinite dimensional feature vector here, okay, and because linear regression can be done solely in terms of inner products, it remains cheap. All we have to do is evaluate this function to create our matrix and invert an n by n matrix. Okay. So let's, well, this is, just one slide. It's just, this is called the kernel trick, right? Yeah, the people from machine learning will have seen this before. We started with some data. Okay, we project it into a higher dimensional space. We do whatever it is we want to do in that higher dimensional space, and then we project back down again. Okay. It's hard to show the kernel trick for regression. So it's normally shown for classification, right? You want to classify these 2 points. They're not linearly separable. You want to use a linear classifier. You project it into a higher dimensional space. Okay, do linear classification there, and project that down. That's the support vector machine, essentially. Yeah. Okay. Well, so kernel regression, non-parameter regression, GP regression, all closely related, and they are all essentially making predictions of new data points that are some linear combination of kernel functions. Okay. We didn't really show this here, but that's all we're doing. Okay. So I'll show a numerical example in a moment. Okay. So let's talk about the example first. Okay. So let's imagine having a rich set of features that are of this form. Okay. So let's suppose we've just got these kind of Gaussian-shaped lumps centered at different points. Okay. I'll show you the picture in a minute. Okay. Then we can show that as we increase the number of features, so let's say we've got, we're just interested in the interval 0 to 1. Okay. We're going to put a feature here, a feature here, a feature here, 3 features. Yep. And we can think about adding more and more of these curves in here. So we can show that as we add an infinite number of these features, and this vector gets longer and longer and longer and becomes infinite, okay, then to work out the inner product between these 2 features just gives us this Gaussian covariance function. So, although I told you you shouldn't call it a Gaussian covariance function, didn't I? Gives you this RBF covariance function. So let's just see this in practice. Okay. So again, I've got R code here rather than Python. So all I've done, I've created some data, okay, and we're just going to have a number of features. Let me just plot them. Okay. So all I've got 10 features here, okay, and we're just going to do linear regression with these 10 features. So where's my feature vector? Okay, here. So for any x, you can read this as pseudocode. Okay, I've just got these values. Okay, so let's just evaluate it. Phi at 0.5. Okay, it's just a set of numbers. It's 10 numbers. It's the value of these curves evaluated at 0.4. Okay, so this curve gives me a value, this curve gives me a value, this curve gives me a value, and so on. So it's just features. Okay. Now I just do linear regression here. Okay. So I've got my beta hat. That's just x transposed x, x transposed y, inverse x transposed y. Yep. So just standard linear regression gives me a value of beta, and I'm just going to plot on what those curves look like. Okay. So instead of a simple straight line curve, you know, a linear regression, it's a curve that looks incredibly smooth and goes through all the points. Okay. And all I've done is kernel regression here, essentially. We can change this by, well, let's do it again. Let's make these these curves, these features. Oops, sorry. What's happened here? Okay. So now I've got really skinny features, yep, and we've got a crappy regression curve, yep. Or I can make really fat features. Okay, so all the curves are essentially the same now over this interval, okay, and we've got something, but not great. Okay, so what we're doing in linear regression, in Gaussian process regression, is making the number of features get larger and larger. Okay. So if I had 100 curves in here, I think it's only plotted 10 of them. Why is it only done that? That's irritating. Yeah, okay. So if we had 100 features, we've got one of these curves nearly everywhere in this interval, or really densely spaced. And this curve is essentially the Gaussian process regression. So Gaussian process regression is in the limit where I take an infinite number of features in here. Okay? And we can't do it in this way because I'm doing this in the kind of the primal form of linear regression. So I'm doing this x transposed x inverse thing here. Yeah? So I can't do this with an infinite number of features. I have to invert an infinite matrix. But when we write it in this dual form, we get the Gaussian process regression. But that's all you're doing is linear regression with this large number of features. Okay. So what does this mean for us? So generally, when we're doing GP regression, we don't think about these features. Okay? We just choose a kernel. So we just pick this exponential kernel or a Matern kernel or so on. But the kernel, your choice of kernel is implicitly defining the features in this vector. Okay? You can think about Gaussian process regression as doing linear regression with these features, okay? And any particular kernel determines what the features are, okay? And what space of functions your model fit lives in. Okay? So by mathematically analysing these things, these kernels, you can work out the features, and that tells you what your resulting sample curves are going to look like. So for RBF kernel, for this kernel, okay, they're very smooth features. These are nice Gaussian bell-shaped curves. We're just adding up bell-shaped curves. Yeah? So what we get are very smooth curves. Okay? For Brownian motion, the features are step functions, essentially. Hence, you get these horrible differentiable curves, non-differentiable curves, etc. Okay. So the idea behind non-parametric regression is that to move us from this kind of very confined parametric shape. Okay? If you're doing parametric regression, you're forced to live in this narrow world you've defined. So you're doing linear regression, you're forcing your curves to have straight lines. Okay? When we do Gaussian process regression, we're assuming your function lives in some richer space of functions in what's called the RKHS, the reproducing kernel Hilbert space. Okay? Doesn't matter. Okay? In a richer set of functions, some combination of these features, and so you've made a much richer class, a much richer space of functions that your true function can lie in now. Okay? And so the kind of belief is, or the hope is, that this richer space of functions we've chosen is more likely to contain an element closer to what we're modelling than the parametric world we might have started with otherwise. Yep. So the parametric constrains us to live in this simple space. The non-parametric allows us to step outside to this much richer class. Okay. So I should ask, are there any questions at this point? I know I've gone through all these things very fast, but yeah. Yeah, of course you can. Yeah. Although, again, Python is the only allowable language in this room, but you can have it, yeah, it's not a problem. I can kind of code in Python, but it takes me about 10 times as long as it takes me in R. So I just couldn't be bothered to put it back into Python. Okay, so the third answer, why use Gaussian processes? And this relates to your question before about skewness. I can't remember who it was who asked it. Okay. So one answer might come from kind of Bayes linear statistics. So has anyone heard of Bayes linear methods? It's really niche. It's essentially Durham, people in Durham who do it. And it's kind of spread out a bit. Okay. But there they think that you shouldn't use probability. You should do statistics without probability. And that we should do it all with moments instead. Because if you're a Bayesian, okay, when you describe your prior distribution, that's supposed to represent your beliefs. Yeah? And when you specify a probability distribution, you're making an infinite number of statements. Yeah? And no one can do that. Okay? So they think we should do everything with just specifying your mean and variance for things. Okay. Doesn't really matter. But they've thought very carefully about how you should do statistics if you're going to do everything with just the mean and variance and no probability at all. So if we only knew the expectation and variance of two variables, x and y, how should we best do statistics? Okay. And so they've argued in lots of different ways that suppose You know the expectation of these two things, the variance of them both and the covariance between them. So just second order properties, yeah, the first moment and the second moment. Then they've argued it in many ways that the best possible choice you can make, okay, the only sensible choice, is that you should use this formula to update your beliefs about x given y. So you started off by having a joint belief about how x and y varied. Someone now tells you y. The best thing you can do is say that your new expected value of x given y is the old value plus the covariance between them plus the variance of y inverted plus the deviation. Okay? And they argue this on coherency arguments. Okay? So this is the only sensible thing subject to some rationality arguments, geometric arguments, all kinds of arguments. Okay? So this argument goes back to Di Finetti, who's the founder essentially of subjective Bayesian methods. But do we recognise this? This is exactly the Gaussian process update. Okay? So this kind of says something about the naturalness of Gaussian processes. Okay? If you're going to do statistics with only the first two moments, just your mean and variance, okay, then this is the best thing you can be doing, and this is essentially a Gaussian process. If you want to do higher order things, like skew is a third order property, or kurtosis, or fourth order property, then you need to do something else. Okay? But if you're just doing it with means and variances, this is the best possible update you can do. Okay? And this is a Gaussian process, essentially. And so kriging is derived, people use it as another word for Gaussian processes and spatial statistics. It was originally derived entirely in terms of moments. Again, they didn't think about Gaussian processes. They just talked about the second order optimal things. So getting minimum variance estimates and so on. Okay, so that's another reason why Gaussian processes are useful. In that, in a sense, if you're only doing the first two, you're doing a second order analysis, you're not worrying about higher order problems. And let's face it, most of the time when we're doing science, we don't have the capacity to do much more than that. Yeah? We can have main effects and a variance is about best we can hope for. Then Gaussian processes are a very natural choice. Okay. Another answer? Sorry, I've nicked these slides from different places, so I've not changed them. The other reason we like Gaussian processes is that they come with uncertainty. Okay? So there are many types of non-parametric regression approaches, splines, neural networks, and so on. Okay? The nice thing about Gaussian processes is that they naturally give you an estimate of the uncertainty in the answer. So you don't just get a point estimate. Okay? If we're doing regression, and we want to predict the value, that can also smooth over your misspecification in some way. So yeah, people do that for sure. The problem we face is that, Neil already talked about it. Whenever we fit a Gaussian process, we have to invert this n by n matrix, order n cubed. Okay? Just doing that a few times can be expensive if you have 10,000 data points. If you want to do it in an MCMC algorithm, it can be prohibitive. Yeah. So, that's kind of the trade-off we have to make, essentially. Any other questions? Please. So this is more relevant in statistics than machine learning, in that in machine learning they'd never do what I'm about to describe, essentially. But in statistics, we often directly want to interpolate points. Okay? So we want a line that goes exactly for all these points. Okay? So what you're doing when you add a noise term is saying, just get as close to all these points. Okay? So the noise is there as a fudge factor, basically. It's there to get you out of the fact that your covariance is misspecified. It just adds a bit of slack so that you can find lots of curves that kind of go through here. Okay? So it just adds you a bit of wiggle room. Does that answer your question? Yeah, okay. So it's not at all principled. It can be principled. You can think you've got a genuine Gaussian error here, okay? But often it's just to kind of ameliorate the effects of misspecification, essentially. Yeah.
Is there like such kind of standard way to like look at this type of problem and solve it, like somehow to automate the process of selecting the anything like the things like prayer distribution or anything like that, to make sure that everything, when you face a new problem, you don't need to like walk several times and try to tune everything based on that. Is there like any ultimate rule that you follow?
People have been working on these auto ML, this automatic statistician project, Zubin Garamani in Cambridge and others, where they try and automate these things. I'm not sure how successful they are. I don't know if anyone else knows. Dealing with the perversities of Gaussian processes in an automated way rather than having a well-trained PhD student.
It just pushes you to a different level where you put biases though at some point, doesn't it?
Yeah, exactly. Yeah.
I mean, you can't get away without putting a model in at some point.
No. So yeah, sure, people have tried automatic kernel selection, covariance function
Well,
selection.
the point is when you're talking about hyperparameter optimization, basically you will have a reward function where you want to optimize, right? But in this case, how do you define that reward function to say what are the things that I want to minimize?
Right. So here I've used the likelihood as my cost function, essentially, and I've minimized the likelihood. And the problem is that the likelihood is the same for these two solutions. Yeah? And because of this complex prior structure I don't understand, the likelihood is the same. Say it again.
The likelihood will be different.
Yeah, but it'll be very similar.
Minimum.
But in this, I think in this case it was very close. And
Yeah, it can be very.
and the point of this example is that it is exactly the same for any solution on this kind of manifold where sigma squared kappa being constant. You can estimate that, but you can make sigma squared bigger and kappa smaller, or vice versa, and the likelihood doesn't change. Okay. And so people, you look at other. This is why likelihood might not be the best approach here. This is why people do things like cross-validation instead to choose your hyperparameters. So you're looking at predictive skill. Yeah, but it's tricky, I think.
Does the use of specific kernels guarantees the convex likelihood?
Does it guarantee a convex likelihood? I don't think so. The likelihood's not convex, is it? No. Nicola's shaking his head, so no, it doesn't. That's part of the problem, right? That's why it's difficult. Yep.
I cannot see why the model are not identifiable by themselves.
Say it again.
You call the problem of non-identifiability of the model, so you cannot actually define the difference between the two, but I cannot see why is that.
Because functions are complex things. You could imagine there being several functions that could fit through the same data, essentially. So, to be honest, I think this result is a mathematical, one of these perverse examples people come up with. But it is a very real problem, okay? In that we're often doing things like adding a Gaussian process to some function, okay? So this could be our model of, my physical model. I want to learn this parameter theta and this Gaussian process discrepancy term, okay, for example. And there's lots of different possibilities here. We could have, many different Gaussian process fits for any different theta, okay? And so we just don't always have this clear identifiability.
So is that coming from because you're using a kernel that brings us in a very high-dimensional space, or is that coming from?
No, this is in the well-specified case, okay? When the true function lies in your RKHS, okay, it's still not consistently identifiable, I believe. I'm not the best person to talk about this, but it's just one of the problems of doing statistics with non-parametric models. So if you ever read these non-parametric papers, all the proofs start with, let's make assumptions 1 to 9, where 1 to 9 are this huge long list of completely impenetrable kind of mathematical statements, and they're essentially to impose identifiability conditions so that you can asymptotically estimate the thing. Okay. To be honest, with Gaussian processes, the biggest problem is dealing with the hyperparameters and the perversity of the likelihood. Okay? But it is a problem with these non-parametric models that we do get lost in the structure. Yeah. Any other questions?
So in this setting, does it help to use stochastic gradient descent when doing the model selection?
Oh, I don't know. Anyone know? Does it help to use stochastic gradient descent when doing the hyperparameter optimization? No.
Stochastic gradient descent is for high dimensions.
Yeah.
And low dimensions, you want to use it. But I think that's a really interesting point. You don't want to use these conjugate gradient optimizers on these very high dimensional neural network spaces, I think, because you'll actually find a minimum and you'll overfit horribly. You wouldn't want to. I think for low dimensions, I don't think they're helpful. I think they would just go slow.
Yeah.
It doesn't even make so much sense because you don't get a gradient. The gradient doesn't decompose into across data points. The gradient is these hyperparameters can't be decomposed into some of the data, so you can't even write it down that way.
Good point. Yeah. Yeah.
Yeah, it can make sense to just take the subset of the data to one step of the gradient descent and then another subset of the data for another step. That would be
You
really
mean for very large data?
yeah, for very large.
I don't think he wasn't asking about. He was asking about if it helps with the minimum. Don't help at all with the minimum.
Yeah, so I think if you want to do the optimization without approximation, where you train to all your data at the same time, then it doesn't help. But what people do in where you have large data sets is you split it up and train on different random chunks. And I think that's what you're saying, right? And that can help. So there's all kinds of progress been made in the past 5-10 years on what you do for large data sets. So now people can train them on millions of data points. Is that fair? Yeah. Whereas what we've described here, you'll get stuck with about 2,000 data points. Yeah. Maybe a few thousand more, but that's about it. So if you want to go beyond a few thousand data points, you have to use cleverer methods that people have been working on recently. Okay. Any other questions?
Is it usual to use another GP to tune the hyperparameter of this GP?
So I know people use GPs to tune their neural network models, right? And to tune their other machine learning models. Have people used GPs to tune?
Mike Osborne's done the Bayesian point pressure.
Yeah, Mike inevitably has.
I think it's less normal to do it for optimization. I guess you could. I don't know necessarily why you would. But you can use GPs for quadrature. So you can fit a GP to the likelihood surface and then try and integrate over the GP. So you get a Bayesian estimate using a GP, which was Tony O'Hagan and what's the
Percy Diaconis.
idea. And Mike Osborne's done quite a lot of stuff with that. Yeah.
I mean, Javier will be talking on Wednesday about Bayesian optimization, and I guess there's no reason why you couldn't use Bayesian optimization to fit your
I think that way it's just because GPU requires large data.
right.
Large set of data.
The reason typically the Bayesian optimization tends to come in when you can't compute the gradients of the surface and whatever, right? So you typically do Bayesian optimization when the function you're trying to optimize, like optimizing over different structures of neural networks, you can't represent it explicitly. So you use the GP as a surrogate model, and then you can do the optimization over that. Whereas you can get the gradients and everything else on this likelihood surface. So for that reason, you don't necessarily need the surrogate, but there might be a reason to do it. I can't think of it at the moment.
Yeah, then you will have another model in which you will have to write the parameters. You could do it by integrating them out and stopping the loop, or replacing an optimization problem with another optimization.
I suppose if you're looking for the global optimum.
Yeah, exactly.
Yeah.
So you can integrate out the
Yeah, that's right.
parameters.
Yeah, because it's eBay or whatever. Yeah. So one about Bayesian optimization, you can use it to try and find to explore wider. So it might get around the problem that would be an interesting one to try actually.
Try what? Sorry.
Try the example you showed with Bayesian optimization to see if you find the true global optimum.
Oh yeah, you could do.
Yeah.
Yeah.
We have a notebook in DeepIO in which we use DeepIO to tune our DeepIO model.
There you go.
Yeah.
Javier's right. So you'll see that. Yeah, you can share that.
Okay. I have another 3,000 slides on computer models and the use of Gaussian processes, but I propose instead to stop. So just to summarise, I told you. I didn't know how long it would take. So there's this great quote in this Gelman paper that came out a couple of weeks ago that GPs were once a good china, essentially, so brought out only on special occasions, but now they're kind of ubiquitous in all of statistics and machine learning. So pretty much any area you think about where people might have been doing kind of regression or something, linear regression, parametric regression before, they're now using Gaussian processes. Or saying that they're using it in classification, they're using it all over the place. Okay? And I think the popularity stems from these 3 points. So basically, the naturalness of the framework, as I say, the second order kind of properties of GPs are what you would do if you only you wanted to just use the mean and variance. So they're very natural in that sense. Okay? The fact they're tractable, we can do stuff with it. Yeah? That's not true for many other models. We struggle to do infinite dimensional non-parametric stuff for any other regression model. And finally, as you'll see kind of from the talks this week, just the empirical success. They've been used now in anger for 20 years, I guess, in these kind of problems. And they're used by huge companies. Pratt & Whitney redesigned all their aerospace design around using Gaussian processes to speed it up. The Formula One teams, Neil's been helping them to do their CFD faster with Gaussian processes. You know, wherever you look, people are using these things because they seem to work well. And they particularly work well where there's uncertainty and you've got small amounts of data. Okay? Neural networks, we all know, work fantastically well. Deep neural networks, if you've got millions and billions of data points. Okay? I'm not interested in that. I'm interested in where you've got hundreds and thousands of data points and uncertainty matters and you've got to keep track of it and so on. And that's where Gaussian processes seem to work particularly well, where you've got limited information. You want to keep track of it as best you can. Okay. Thank you. Lunch.
You mentioned a paper
Mm-hmm.
by Tony Hagen or something?
Yep.
What's the name of that?
It was Bastos and O'Hagan.
Bass.
I'll write it if you like.
Yes, please.
Yep. That will. I think that's the only thing they published together, pretty much.
Okay.
It's somewhere between about 2008 and 2011ish, and I'm pretty sure it's in Technometrics. But it's been cited a few hundred times. It's easy to find.
Okay, great. And will we get the slides from the summer school?
Yes, they'll go online. Yep.
Okay, nice.
I'll put them online.
Okay, cool.
No worries. I might cut out the 3,000 at the end.
Leave them, please.